Welcome to the GOTO podcast. Each episode covers the brightest and boldest ideas from the world's leading experts in software development. Tune in for practical lessons, compelling theories, and plenty of inspiration. GOTO gathers the brightest minds in the software community to help developers tackle projects today, plan for tomorrow, and create a better future. Stay up to date with the latest in tech through GOTO's top-rated events held online and in person in cities like Amsterdam, London, Copenhagen, and Chicago, and by subscribing to the GOTO Conference's YouTube channel, where you can find thousands more high-quality dev talks. Learn more at gotopia.tech.
Hello everybody, I'm Olimpiu Pop, Technologist, and probably I can call myself a tech journalist as well. And I have in front of me Andrew Lamb, another technologist that knows at least two very complicated things on my side. And those are databases or data systems, probably to be more correct. And the other one is C language. Well, Andrew, I think it's better for you to introduce yourself, please.
Oh, yeah. Thank you, Olympia. I'm very excited to be here. I am a staff engineer currently at InfluxData, but in that context, I work a lot on databases, specifically the analytic database stack, and I'm sure a lot of stuff we'll talk about later. My background was basically as a low-level systems programmer. So that means like databases and compilers kind of stuff. I worked for many years at a company called Vertica. I worked in Oracle. Vertica was one of the sort of first wave of commercializations of these sort of shared nothing distributed database architectures. And then I've worked in various other sort of engineering and data platform teams. And now I work on InfluxDB3 and the core engine that drives that, including the SQL engine, which is built on top of the big pile of open source, including Apache DataFusion, Apache Arrow, where I'm the PMC. I'm on the PMC for both of those projects, and I'm down in the guts sort of on a day-to-day basis. So I really love that stuff.
Thank you. Thank you for loving it, because then we don't have to love it and just play with it on top of that. We had other conversations, and one of them was together with Felix, which unfortunately cannot join us. And what we spoke is that on other parts of the programming universe, we can take bits and pieces. We have multiple frameworks. We have libraries that we can just place them together and have a final system. But until not long ago, that wasn't the case for data systems. And that's what was the conversation that we started as a trio, that Kafka played a role as one of the parts, at least for ingestion systems for data systems. And then we had different engines like RocksDB or DuckDB. But when you rebuilt InfluxDB with its third version, you made a couple of changes. One of them was using another programming language, and that's Rust, as we spoke about. And the other one, you coined the term FDAP. Can you please elaborate about what's FDAP? Or should we add the I as well, or not just yet?
Yeah. I for Iceberg, probably. Yeah, so the FDAP Stack, I want to say, I wrote the blog post, but like really it was the CEO and CTO of Influx that came up with that, right? So Paul Dix is the CTO of Influx, and he saw early on that perhaps probably because he wanted to go write yet another version of the database, right? And the CEO was like, how are we ever going to possibly afford that? Because it's a big, expensive undertaking, which they knew firsthand because they'd just gone through it, right? And now they want to sort of rework everything from the ground up. Paul's vision at that point, and the pitch was, we don't have to rebuild everything from the ground up, because by this point, people have built these analytic systems and done it enough that the common patterns are emerging. And so at that point, he identified the technology, specifically Flight, Apache Arrow, Flight, which is part of Arrow, DataFusion, and Parquet, as technologies that you could build a whole new sort of time series database on top of. That's what Influx is, without having to reinvent everything, right? And Paul was definitely on the earlier side of that trend, but the idea was, rather than have to build a database from scratch, which by the way, I did it, Vertica, and I saw it was like a 5-year endeavor with like 20 engineers, right? Like it's a major investment, like good engineers too, like PhD and database kind of things. But since that pattern has now been implemented so many times, the thesis was we understood where the boundaries were, and we could really focus people's efforts together to not have to reinvent the same thing over and over again.
Okay, so because you made a mistake and told me that you already have the experience of building everything from scratch. Let's take a step backwards then and just maybe think about it. What are the conceptual pieces that usually will come and will just say that these are the building blocks for a normal data system, and then go back and map them and see how it actually moves from, I don't know, ingestion via the memory model and then on the file system and then back again. So
and so I'm going to talk from the perspective of a database implementer, right? Like someone who's building one of these components that you would then build an actual data platform on top of, right? So I'm going to talk about how you would implement a database, and depending on you as a user, when you're actually trying to assemble this into some either data platform or higher level application, there's often you would use pre-assembled components, right? So I'm going to talk about how you would implement stuff like InfluxDB, not how you'd implement an application on top of, or likewise with Kafka or whatever. And actually some, the line there is always a little blurry, and I think it's getting more blurry as we go, in the sense that it's easier to decide where exactly where you want to work on. Maybe we'll talk about that later in the call. But at the high level, like when you're going to build one of these high performance analytic systems, the best practice in the last probably 20 years came out of the research world is a very simple concept, which is you store it in columns, right? Like, which basically means, this is mostly in the context of storing tabular data, right? But the same concepts apply to other forms. So storing relational tables, you can either store all the values in each row next to each other, right? If you think about a spreadsheet, or you can store all the values in each column next to each other in memory. And it turns out for analytic processing, for a lot of reasons, doing the column store is a much better choice, specifically because it can take advantage of modern hardware like vectorized execution, right, which does phenomenally well when you just have the same operation to apply to a lot of different data items, versus row-oriented. You kind of would have to be continually changing what the application. So there's basically a shift. It started probably 20, 30 years ago, starting in academia and moving into really move columnar technology into databases. And so these days, if you're going to go build a new database system, to your point, you would typically need to have some way to get the data from your client, and you have to represent it in memory somehow. And in particular, you have to be able to do operations on it quickly. The other thing you need to do is of course, so that's what Apache Arrow is basically designed for. And I wouldn't say Apache Arrow is really earth-shattering in terms of its technical content, right? Those ideas have been around, and there's really not that many ways to represent an array of 64-bit integers right in memory. But what's important is that everyone agrees on how it looks, how to pass the metadata around, how you represent nulls. A null mask or a validity mask doesn't really matter, but it matters a lot that everyone agrees on what the mask means. So anyway, having a standardized, what I think Arrow's real value was, its standardized best practice across columnar representations.
Okay, so let me just stop you here to just translate it for a 5-year-old and see if I got it correctly.
Yeah, sorry.
So no worries. That's why we are here. So what you're saying is that in the last 20 to 30 years, we had a transition from the normal way, how we thought about databases, to looking, especially in terms of analytics, to just look at them in terms of columnar data, because that made sense also in terms of extractions, but also in the way how we can store it and how the new hardware behaves lately, as it will be much more efficient, right? So after that, what you mentioned is that Apache Arrow takes care of that memory model. Nothing earth-shattering, but it just takes care of a couple of it depends, because we love to use it depends on multiple levels. Yeah. But from that point of view, what it actually does, it just comes, sets a standard, and then all the things that you normally want to think, what would be the sequence of data types, and probably the way how we store it, how we represent null or other aspects are now standard, and then we can build on top of this abstraction. And that will be easy to go. So with each iteration, it will just improve, and then everybody will use the same standard.
Yeah. That's a very good summary.
Great, thank you, Andrew.
And I just wanted to maybe I can take a step back just a little higher too, to try to describe why the transition to column stores happens, right? At a really high level, philosophically, when computers and databases were first coming around in the 60s and 70s, there wasn't that much data in them, right? Not a whole lot of the world had been digitized. We weren't creating massive amounts of digital information at that point. And so the speed of getting data in and getting data out was typically happening at, individual, like it was based on human actions, right? Like you did something to your bank account. And so that fundamentally sort of, like that's as human scale, both reading and writing. Then what happened in the 90s, 2000s is an increasing amount of both our lives and also all the computing infrastructure became digitized. And so it generated huge amounts of data, right? That didn't just come from human scale systems. It came from machine scale systems. So the volumes of data were much, much higher, and we needed new techniques to keep up with the increasing data volumes. So that's around the time when columnar technology really took off, because we needed better ways to basically handle the ever-increasing data volumes. And now, of course, there's some theories we talk about to move into AI, but that's maybe a different conversation. So anyways, so Arrow is the in-memory representation for any database. You need a way to actually manipulate the data once you get in there, right, to actually compute the calculations people ask for. And you kind of touched on it, but I wanted to highlight it again. Arrow really has two things that are going for it. One is that it's standard. So what that means is you can pass data without having to translate the format from things like data frames to a database, to another database, to like basically it lets you easily pass data between systems without paying the serialization cost of having to translate it back and forth to different formats, which is actually, I think, the original reason why Arrow was founded. But I think a hugely important other aspect that we talked about that I think is really critical for system design is when you're designing this, no longer have to go through the trouble of like deciding exactly how you're going to represent timestamps and where the time zones come in and how you're going to convert it and what kind of date you have. Like a bunch of this stuff is not impossible to solve, but I'll tell you from experience, it takes a huge amount of time and effort to actually work out all the details. And so the fact that someone else has done that already just basically accelerates your development cycle a lot. There's a whole bunch of infrastructural work you just don't have to do because you can just take advantage of what's already there. And I think that's pretty huge.
Okay, so this would be the things that we'll have in the memory. But usually we call them persistent because they stay somewhere where we can find them afterwards.
That's right.
And that's probably Parquet, right? How do they interconnect? How do you make the connection between the two of them?
Yeah, so they're different technologies, but they're both columnar technology, I would say. Parquet is designed for persisting data. In particular, it has a bunch of encodings and compressions so that the data volume on disk or that you have to transfer to the network is significantly lower. So in order to process things in memory, right, you have representation that's convenient to process, but if you want to save that for long-term archival storage or share it with people or store it on S3 or whatever, you end up with Parquet. Does that make sense? So it's a columnar file format and it's designed for storing large volumes of data efficiently on disk. And I think it has a couple of benefits over the alternative, right? Like, well, one option is you can build your own whole file format, which you have ultimate freedom, but it's very expensive. Another classic alternative was CSV files, right? You just dump a bunch of CSV files. There's a couple of problems with CSV files or JSON files. Similarly, they're not particularly well compressed, so they're very space inefficient, both for like your storage costs, but also the amount of time it takes to transfer. If you want to read a CSV, it actually takes a lot of effort to extract the data out of the text form into the form that you want to process, right? Because you have to like parse strings into numbers, which is a very, very expensive operation. And the final thing is it's actually, they don't have type information attached to them, right? So you basically have to, when you get a CSV file, you have to figure out, is this column full of dates, or maybe it just kind of looks like dates, or maybe they're UIDs or like, so, and every system sort of has to do that schema inference itself. And of course they're a little incompatible. And so there ends up being a bunch of pain when you have to get systems to go. So Parquet has its own type system. It's got a very efficient encoding and compression scheme in there. And now it's a standard also sort of governed by the Apache Software Foundation. So you have lots of vendors that support the file format.
Sorry to be tricky, but CSV and JSON are not exactly earth-shattering again. So comparing them, Parquet with that, I cannot say that I'm wow. But maybe we can underline one other thing that Parquet has that allows it to be that important in the new data landscape. What I think it's probably very important is the fact that a lot of other projects are already adopted it. So that means that most probably You can use it also in terms of interconnectivity between across the board in more multiple data projects. Did that make a difference for you while implementing it? What would be a couple of benefits as you as a provider of databases have with that?
That's right. Yeah. So there's two primary benefits to Parquet. The first is that it's compatible, that you can write a Parquet file and read it with other tools. Both helps if you want to transfer data, like how your customers migrate their data in bulk, either into or out of your system. It's very helpful for that. Especially so if you don't have to rewrite it internally, you can just give them the internal Parquet files was the theory. Other major benefit, which goes back to the original discussion, is the amount of effort that's gone into these open source Parquet readers and writers is actually quite high. And so, while if you had your own custom file format, which is what you would typically do actually in a database, to your point, right? Like you don't typically store data in a database on CSV files, right? You have some custom proprietary format is a more common thing. And the upside of that is you can custom make the file format however you want. The downside is you also now are on the hook for implementing it, maintaining it, and optimizing it, which again is not impossible. And if you had an infinite amount of resources, you for sure could make something better than Parquet. But the fact that Parquet in my mind captures like 90% the value of what you get out of your own custom binary file format, plus it's already had lots and lots of other people working together to make it fast and interoperate and integrate with all these other systems, means that you already start significantly ahead of where you might realistically be able to go if you're starting everything from scratch yourself.
Okay, great. So this is both Arrow and Parquet are taking care of storage at different levels. So Arrow is in the memory space, so that's volatile. And then it's about persisting it on the file system. So these are the 2 points. The other two Mrs. letters from the acronym from FDAP are DataFusion and Flight, right? One of them is a query engine. Well, that's pretty obvious what it does. The other one is a network protocol. How does the Flight come in between these pieces?
So as the rise of networks, networks became faster and faster over the last 10 years, about 20 years really. Of course, when that basically means almost all databases these days are either distributed or they're doing some sort of client server. So you have to send the data over the network. If you have to design a fast protocol that's efficient to send large amounts of columnar data over the network, you can certainly do it, but it's not going to look all that dissimilar to Flight. So basically, Flight allows you to take these arrow arrays and quickly, without having to spend a lot of time preparing the messages or preparing them when you receive them, you can just send efficiently the arrow arrays over the network. So I think that really allows now you to build distributed systems with this toolkit, right? Which, Influx 3 has a distributed component, rather than us have to go re-implement yet another protocol, which is probably going to look about the same as what Flight does under the covers. We can just take advantage and reuse the existing components that are out there. And realistically, Influx is not just using these, it's also actively contributing back. Like that's a big chunk of my job, is to help organize and drive forward the open source implementations. But it's not just an altruistic donation on Influx's part. The idea is that by strengthening the community, getting other people to contribute as well, we're effectively able to get access to technology that we wouldn't be able to afford to develop entirely by ourselves.
Yeah. What I think Paul was mentioning at some point is that it's one of the benefits of the open source communities where you're just building, and especially in the database space, there is a lot of academia that is needed and a lot of research. And rather than doing that and reinventing the wheel over and over again, you're benefiting. And through the open source community, you have all the knowledge that you need and you just put them in place. And it seems that it's the obvious step also for the data system, the data ecosystem, because usually this remained a bit behind, because we know it's like in a lot of spaces, we can be an early adopter, but data needs to be persistent and you cannot lose it. So then this is my feeling that it's important that we got here, and just tying them together allows us to have all the building blocks that we want. And through a open source community, it's a lot better, given that also more eyes on the same source code allows you to ensure that it's safe and to be used. But
yeah.
Now I have one more question for you, because as you said, you worked on databases for a long period of time, and we were discussing about distributed data systems, right? And on one hand side, what I was taught, I don't know, during university years a long time ago, it was all about ACID and how important it is, a database, relation databases, that data is there and it has all the ACID properties. Now, on the other hand, we have the CAP theorem for distributed systems that says that we have to pick two out of all the three letters. How does this all fit together to just make sure that you don't lose data and all the things that you actually need to just ensure the expectation I'm just thinking now also in terms of you having time series and you have to see trends.
Yeah.
How do they fit together?
I'll talk about time series in just a second. I think what you see is that different people in different use cases actually have slightly different trade-offs that they want to make, which sounds obvious, right? But I think it's part of why you saw the growth from like a few very monolithic databases like Oracle and SQL Server, whatever, right? Which are still huge businesses, great products. But what you've seen in the last like 10, 15 years is just an explosion of other database types, right? There's a lake-based type, but there's also a whole bunch of little startups making databases. And that's partly driven by all these open source components, which we're talking about. But I think it's also a acknowledgement that the people are willing and able to spend money and time and effort optimizing for their particular use case. So like the ACID properties that Oracle offers are actually they're not the same type of properties that people want out of time series database. The major differences from time series, like a special purpose time series database, what do you get? It's obviously built around time, but what does that really mean? I think the major features I've seen are when you put data in, you don't have to define the schema up front, right? Something like Oracle, MySQL, Postgres, you have to like specifically specify up front what all the columns are, what their types are before you can put data in. So time series database, you can typically just load it directly and the time series database has to figure it out. Another major difference in time series database is that there's a huge drop off in value. So like a lot of times people are using time series databases to capture like metrics or information from their production systems. And it actually turns out that stuff's not very, like your production metrics from 2 weeks ago are nowhere near as valuable as the production metrics from like 30 seconds ago. And so there's a huge amount of effort that's required to efficiently get the data organized, able to be queried when it gets in, but then also quickly move it out of the system and stop paying lots of money. If, like you want to put it on RAM, for example, for like the last 2 years, you just can't afford it. So there's a lot of sort of like data lifecycle management that happens that for a big database, typically you wouldn't be doing it at the same granularity. Like Oracle, you'd have monthly partitions, maybe you just drop the storage and reclaim the storage every month or something.
Okay.
And then of course, I don't know if you ever tried to write time series queries in SQL. They can be pretty terrible. And so Influx also has a special, and many other time series databases also have special query languages that are much less cumbersome to express common time series operations like gap filling, for example, which is not realistically in any SQL standard.
Okay. Thank you. Thank you for all the insights. Andrew, last question from my side before we wrap up. What's in with the D? Because that's the query engine. As you said, it's nice to store data, but at some point we need to take it out because in the end, that's the benefit.
Absolutely. And, and also building, so there's the D stands for DataFusion, Apache DataFusion. It's another top level Apache project. It's a query engine, as you said. What that basically means is you can give it data. It can read Parquet files, or you can give it data, any data source that feeds arrow record batches. You can run, it'll plan SQL queries for you with the full on optimizer, all the bells and whistles. Right? It'll make a nice fast plan. And then it's got a bunch of optimized execution operators, which we could talk at length about. But that's another example of like, people basically know now how to implement fast vectorized execution engines for SQL. We did it whatever it was 15, 20 years ago at Vertica. They did it again, and it happened again in the sequence of products from the Hadoop era, right? Like Impala had one. A bunch of other examples from the Hadoop ecosystem have similar tech, they're not the same code, but it's a similar technique. DuckDB now has one, right? This is all innovated in a product called MongoDB X100, I believe is the paper name. I think it might have been eventually it was called VectorWise, I think, when they spun it out. But basically, the point is, it's been like two generations of commercial products based on this, right? So like building another third whole set of distinct engines seems really quite silly because they're all basically look the same. And so DataFusion is basically that vectorized query engine that we are able to get a lot of people using. It's written in Rust. It's all great stuff, but it basically just implements all of the well-known but still complicated, like taking a lot of effort to implement optimizations for running a SQL query engine, which not just SQL, but any sort of relational query engine, which I could wax philosophic about, but it's probably a whole topic for a whole other podcast.
Yeah, that sounds quite interesting. So if I get it correctly, well, obviously for decades we had the SQL movement, and that was, as you said, huge piles of money that was split in between the giants. Then there was the NoSQL movement that was trying to democratize everything and do a lot of stuff that wasn't actually the greatest approach, even though the companies appeared from that point on. But now with the whole movement, we have bits and pieces that will allow us to tie them together to get exactly what we have. And for me, probably the most important aspect is the ability of querying in SQL these nuggets of data that are columnar stored. And that makes probably the best takeout from all this landscape. But I know that you have one more ace in your sleeve, and that's Iceberg. That's probably on the roadmap. I don't know how far along is it, but I know that Iceberg was close, as also the name says. It's about large data and ability of touching that. Can you briefly share something about it?
Absolutely. What's happened in the analytic database landscape over the last, 5-10 years is that the dominant architectural pattern that you see is persistent storage on object store, which basically means you have to store Parquet files on S3. And the reason people do that is because it's or AWS S3 or the equivalents from GCP and Azure. And the reason people do that, it's called the disaggregated database architecture, right? So you basically outsource your durability to S3. S3 is great. I don't know if you're familiar with S3, but it's basically the infinite FTP server in the sky. It's kind of cheap. It's not as cheap as it used to be, but it's cheap and it's durable. So from a database perspective, it frees you from having to worry about scalability or durability concerns, which can be very complex to implement. And so how Iceberg fits into this is, as people started, more and more of your data lives in Parquet files on object store, right? And there's huge piles of it. The question now becomes, how do you let other systems read and write that? And I think many of the early systems had their own sort of custom, basically second database, like they call it a catalog, which basically tells you how to, which Parquet files make up what table. And Iceberg is attempts to standardize that in a way that now you can have multiple systems, both reading and writing data that is stored in this sort of cheap, durable storage on S3. And so the promise of something like Iceberg, I don't think we're quite yet at the realization, but the promise is you can basically have Iceberg be the core system of record where all your data lives, and you can have a whole bunch of specialized data processing tools that live outside, and each are able to access the same data, and you don't have to have like an ETL process that moves the data back and forth between the systems. You just have sort of one centralized repository of data, and that lives in open file formats like Parquet, and Iceberg defines how to find the tables reasonably efficiently. And then you can have, if you want some custom AI tool to read it, you can do that. You want BI dashboard tool to read it. Again, you want big distributed SQL database to read it. You can do that. So that's the vision. I don't think we're quite at the vision yet, but the vision is you can basically you can have a database that's shared, or the data files are shared across different systems.
Okay, great. So if I got it correctly, for a long period of time, we had data pipelines, ETL pipelines that were taking care of all the phases. Then we had the other side with reverse ETL. And now with Apache Iceberg, probably we'll have something that is much more efficient, where you store the data and then it's easy to extract regardless of the space where it's coming from. Did I get it correctly?
I mean, that's the pitch, right? But you might imagine.
Okay. There's
a bunch of vendors that are very interested in, who controls what part of your data pipeline. And so I would say there's a lot going on in the space right now.
Okay. So let's meet in 1 or 2 years and see where the pitch got it. Okay. Thank you, Andrew. Anything else that you would like to add, something that we missed?
No, thank you for having me on. This is great. I know we had a lot to cover. It's an exciting time to be in databases.
I'm sure that we'll talk again. Thank you for your time. Have a good one.
Thank you very much. See ya.
Thanks for listening to this episode of the GoTo podcast. Head over to gotopia.tech to discover lots more content from the brightest minds in software development.